Right, hello everyone. Today we are doing the similarity theorem proof. This is the second Euclidean geometry proof that you need to know. So the similarity theorem is something that we've actually been using since grade 8, grade 9, but now we have to prove it. So they're saying if two triangles are equiangular, then the triangles are similar. Now we know that already. But what we actually are saying, what the definition of similar triangles actually entails here is that if two triangles are similar, they are both equiangular. So equiangular and their sides are in proportion. That's actually what the definition of similar triangles states. So what we've been doing when we've been proving that triangles are similar, we have just been showing that they are equiangular, and then we've actually been using this theorem that states that if two triangles are equiangular, then they are similar. But in order to prove this theorem, we actually have to prove that both of these conditions are met, because that is actually what satisfies the conditions, or these are actually the conditions of two triangles being similar. They have to be equiangular and their sides have to be in proportion. Okay, so this is what we're going to prove essentially. We are going to prove that their sides are in proportion. It's given that they're equiangular, we have to prove the second bit. So this is the diagram as it will look probably. They will give you two triangles, and of course they can give you different letters from the ones that I've used here, and you will need to adjust your proof depending on the letters that they've given you. So I'm just going to write down here given. So we are going to say that triangle ABC and triangle DEF are given. But it is also given that they are equiangular. So as we can see here in the diagram, it's given that angle A is equal to angle D. Angle B is equal to angle E. And angle C, across, is equal to angle F. Alright, so that is the full given statement. Like I said, they can give you different letters. You need to then adjust that. But the given statement is also always written down for you. Now, what we need to prove, the required to prove, or RTP for short, is that these two triangles are similar. But like I already explained, in order to prove that, we need to prove that both conditions have been met. They are equiangular, which is given, but also that their sides are in proportion. So we are going to have to prove that this side, AB, over the corresponding side in the other triangle, DE, is equal to this second side over the corresponding side in the other triangle, so AC over EF, and that is then also equal to the third side, which is BC over the corresponding side in the other triangle, so BC over EF. So this is actually what we are going to prove, and then once we've proved that, we're going to say, therefore, triangle ABC is similar to triangle DEF. Now, of course, we always have a construction. This construction, you need to be able to write out in words, and you have to indicate it on the diagram. For construction, we are going to say on AB, mark P such that AP is equal to DE. So what we're going to do is on AB, we're going to make a point. We're going to call that point P, so that AP is equal to DE. So you can see here that I have gone 3 blocks down from A to, well, actually from D to E, that's 3 blocks down. So you need to make sure that when you are constructing point P, you are also going 3 points down from A. Then we're going to do the same thing on the other side. So on AC, we're also going to construct a point here. We'll call it Q, so that this side, DF, is the same length as AQ. And then we are going to join points P and Q to each other. And that is a construction. I'm going to continue writing it down. Okay, so on AB, mark off P such that AP is equal to DE. And on AC, which is this line, mark off Q such that AQ is equal to DF. And then we're going to join PQ. Okay, that is the full construction. Now, just quickly, I'm going to talk you guys through what the proof is going to entail, and then we are going to write it down. It is quite a long proof, but it's not too complicated. What we're going to do is we are actually going to prove that these two triangles, this one here, triangle APQ, and triangle DEF, are congruent. Now, in order to do that, we're going to use side angle side, because when we constructed point P, we constructed it so that AP is equal to DE. So our reason for that is going to be construction. Then we have that angle A is equal to angle D. That was given. And then we have that AQ is equal to DF. That is also because we constructed point Q to lie at a point so that they will be equal. So we are going to use side angle side to prove that these two are congruent. Then once we have that, remember that when triangles are congruent, that means that they are identical. So this angle at E is going to have to be equal to that angle at P, angle APQ. So that is going to be our next step. We are going to state that APQ is equal to angle E because of congruent triangles. But then, guys, what we have here, I'll just use a different color, is we actually have an F shape over here, right? We have corresponding angles that are actually equal in our triangle here. And when corresponding angles are equal, or I should rather say corresponding angles can only be equal if they lie in or on top of parallel lines. So that is going to mean that PQ is parallel to BC because of those corresponding angles being equal. Once we've stated that PQ is parallel to BC, guys, we can use prop theorem in this triangle because now we have parallel lines over there. So if we look back at what we're trying to prove, I'm looking at this first fraction. I need that first fraction in what I'm proving. So we are going to say AB, which is this whole side, over AP, which is this smaller side, right, is going to be equal to AC, which is that whole side, over AQ, which is that smaller side. But then, look, we're actually trying to prove that these three fractions are equal. We'll get to the third one later on. But to prove that these first two fractions are equal, I think I might have said angles. Sorry, I'm in fractions. I'm going to say again, because of prop theorem, we're going to say the whole side over AP is equal to that whole side over AQ because of prop theorem. But guys, DE is equal to AP. So where I have AB over AP, I'm going to replace AP with DE because they are equal. And then on the other side, I'm going to say AC over AQ. Remember, DF is equal to AQ. So then we're going to replace AQ, which was in the denominator, with DF. And then we have our first two fractions equal from that. Yeah, I'm just going to erase those markings because I'm going to have to do some more later on. All right, so that is basically how the proof works for the first two, and then I'll explain how we're going to bring the third fraction into the mix. Okay, so for proof, First, like I said, we are going to prove that these two blue triangles are congruent. So I'm just going to write in triangle APQ and triangle DEF. First thing, like I said, is that AP is equal to DE, and the reason for that is construction. Right? We even have it over there in our construction line, such that AP is equal to DE. The second point is that angle A is equal to angle D, and that is given. There we go, it was given up there. The third point here is that AQ is equal to DF. That is also because we constructed them to be equal. It is written there in our construction in the second line. Therefore, triangle APQ is congruent to triangle DEF, and the reason there is side angle side. Okay, so now we've proven that they're congruent. Now we're going to say angle APQ is equal to angle E because of congruent triangles, but that means that angle APQ is equal to angle B because these two are equal as well. Therefore, PQ is parallel to BC because of this F shape here, because of corresponding angles being equal. All right, so now we're going to say, therefore, APQ is equal to angle E, and our reason is congruent triangles, and angle E is equal to angle B, that was given. Right, these two angles are equal, so therefore, if this angle is equal to E and E is equal to B, these two angles are equal to each other. So therefore, APQ is equal to angle B. Therefore, we don't need a reason for that, that's just following on from the statement. So therefore, PQ is parallel to BC, and the reason for that is because of the F-shape corresponding angles equal. Please, you have to write the word or the symbol for equal there, otherwise you're not going to get that mark. Okay, so now that we know that these lines are parallel, we're going to say AB over AP is equal to AC over AQ, Crop theorem. But AP is equal to DE and AQ is equal to DF construction. Therefore, we're going to have our first set of fractions being equal. Therefore, you don't have to leave lines open like I have. I just find it makes it a bit more easier to, or yeah, a bit easier to follow if you do it like that. So now I'm going to say A, B, the whole side over AP, the top part of that side is equal to AC, the whole side over AQ. Again, the top part of that side. The reason for that is crop theorem. And remember, for crop theorem, you have to state which lines are parallel. It's the two lines that we proved parallel in the previous step. So PQ is parallel to BC, but AP is equal to DE and AQ is equal to DF. That again was because we constructed them to be equal, so your reason for that can just be construction. Therefore, we can now replace AP with DE over here and AQ with DF over there. So therefore, AB over DE is equal to AC over EF. Again, we don't need a reason for that line. That is just following on from the two previous lines where we've just substituted AQ for DE and AQ for DF. Okay, so that is the first two fractions of our of our sets of three fractions that we need to prove equal. Now, for the third fraction, what we're going to do is actually we're going to prove that these two fractions are equal. Because if I have that AB over DE is equal to this fraction, and then I have that this fraction is equal to that one, that means that all three of them must be equal. Now I have good news. In order to prove that these two would be equal, we would follow the exact same steps. But what we would do is we would construct, I'll do it in red, a line, and this is possibly not to scale, but we would construct a line over there so that this triangle is congruent to that triangle, right? So instead of working with the top triangle there, those two congruent, we would construct a point on AB so that this, say we call that S, for example, and T, so that SB will be equal to DE and BT will be equal to EF, and then we would follow all the exact same steps. We would again prove that this triangle is congruent to that one. Then you would say, okay, this angle at T, for example, is equal to that angle at F because of congruent triangles. So therefore, those two angles are equal. So therefore, these two lines will be parallel. So then we can use prop theorem here. And then we can again replace the sides that are equal. So we would follow all the same steps. And luckily for us, when that is the case, we do not have to rewrite all of those steps. We can just say similarly, and then we just need to write what the construction would be. And then we can just say we can prove that these two pairs of fractions are equal. And then we can end off our proof. So that's quite nice. All right, so for the third pair, for the third fraction there, we're just going to say similarly by constructing, and now you can just choose whichever letters you wish. I'll say S on AB such that, oh sorry, that's off the screen, I wasn't aware. Similarly by constructing S on AB such that, move this across a bit, SB is equal to DE and T on, because that other side, the bottom side was BC, such that BT is equal to, let's just double check. So I want to have point T over here somewhere so that BT would be equal to that side there, so EF. We can prove that AC over EF is equal to BC over EF. Therefore, we can actually state that all three pairs of fractions are equal. So now we can say AB over DE is equal to, I'm just going to copy this, equal to the other two fractions. And then finally we are going to say, therefore, triangle ABC is similar to triangle EEF. And what I would like you to write is equiangular and sides in Okay, that is the end of the proof. So guys, they might ask you just, instead of in the required to prove, they might not say triangle ABC similar to triangle DEF. They might just give you the three fractions, right? In which case you would end after stating the three fractions. They might even be kind and they might just state the first two fractions, not all three. I've seen that in final exams where they just give two of the three fractions. Because this, yeah, it seems a bit silly to expect you to write all of this stuff here at the bottom. So you might get something like this, in which case you would end by just listing those two fractions. But guys, you do have to be prepared to add the third part. So please make sure that you remember the similarly part. And you have to say which point you are constructing where such that which parts of those lines will be equal. That is very important.